Have you ever really thought about a simple water molecule? It's a perfect example of something we see everywhere in nature, an electric dipole. It's this tiny little system that has a positive end and a negative end, even though the whole thing is electrically neutral. So the big question is, how do we figure out the electrical influence, what we call the potential, that one of these dipoles creates at some random point out in space? Well, that's exactly what we're going to break down today.
Here's our game plan. First, we'll nail down exactly what an electric dipole is. Then, we'll get our hands dirty setting up the geometry of the problem. After that, we'll walk through the step-by-step derivation of the potential formula, the fun part. Then we'll explore what that formula is actually telling us about the real world. And finally, we'll wrap it all up with a summary of the key takeaways.
All right, let's kick things off with Section 1. What exactly is an electric dipole? We need to get this core concept down first.
At its heart, an electric dipole is really simple. It's just a pair of charges, one positive, one negative, but with the exact same magnitude, which we'll call Q. They're separated by a fixed, usually tiny distance that we call 2a. Now, if you add up the charges, plus Q and minus Q, you get 0. So from far away, the dipole looks totally neutral. But when you get a little closer, that separation makes all the difference. Even with a total charge of 0, that little gap allows the dipole to create an electric field and, as we'll see, an electric potential in the space around it. So how do we measure the strength of a dipole? For that, we use a concept called the dipole moment, which we represent with the letter P. Now, this is a vector, meaning it has both a size and a direction. The size, or magnitude, is easy. It's just the charge Q times that separation distance 2a. But the direction is a super important convention you have to remember. The dipole moment vector always points from the negative charge toward the positive charge.
All right, so we know what a dipole is. Now let's set the stage so we can actually calculate its potential. This next part is all about getting a clear picture of the geometry.
Okay, let's break down this diagram. It might look a little busy, but each piece is important. Here are our two charges. We've got plus Q up here and minus Q down here. The total distance separating them is 2a. Right in the dead center, we have our origin, point O. Our whole goal is to find the electric potential at some random point in space, which we're calling P. Now, the distance from the center of the dipole, O, out to our point P is R. The distance from the positive charge to P is R1, and from the negative charge to P is R2. And finally, this angle theta is absolutely critical. It's the angle between the dipole's axis and the line connecting the center to our point P. And now for the main event. Let's walk through the math to get the formula for the dipole's potential. Don't worry, we're gonna take this one logical step at a time. It's like solving a little puzzle. You know, one of the great things about potential is that it's a scalar. It's just a number, no messy directions to worry about. And because of that, we can use a really powerful rule called the superposition principle. It just means we can find the potential from the positive charge, find the potential from the negative charge, and then just add them up. Simple as that.
So, when we apply that principle, this is the equation we start with. The total potential, V, is the charge Q divided by this constant, 4 pi epsilon naught. That's just a fundamental constant of the universe. And all that is multiplied by the difference between 1 over R1 and 1 over R2. Now, the real puzzle here is to figure out how to rewrite R1 and R2 in terms of things we can actually measure, like that distance R and the angle theta.
If we look back at our diagram, you can spot two different triangles that are formed by the charges and our point P. And whenever you have a triangle that isn't a nice, simple right-angle triangle, and you need to relate its sides and angles, there's a classic tool we can pull out of our geometry toolbox, the law of cosines. And when we apply the law of cosines to each of those triangles, we get these two expressions. They look almost identical, don't they? The only difference is the sign right before that last term, a minus for R1 squared and a plus for R2 squared. This makes perfect sense, and it's all based on the geometry of the angles inside each triangle.
So we have our equations, but they're still a bit messy to work with. This is where we get to use a really clever shortcut. In the real world, we're almost always interested in the potential far away from the dipole, where that distance R is huge compared to the tiny separation A. And this physical assumption that R is much, much greater than A lets us use a mathematical tool called the binomial approximation. It's a lifesaver that lets us ignore tiny, insignificant terms and simplify the math in a huge way. Now, the process has a bit of algebra, but the core idea is simple. We rearrange the equations to get the 1 over R terms that we need. Then, because A is so tiny compared to R,
any term that looks like a squared over r squared becomes practically zero, so we can just throw it away. Applying the binomial approximation cleans up the rest, and suddenly we're left with much, much simpler expressions for 1 over r1 and 1 over r2.
And after we plug those simplified terms back into our original potential equation, and we remember that the dipole moment P is just Q times 2A, we get this. This is our aha moment, a beautifully simple and elegant final formula. The potential V is equal to the dipole moment P times the cosine of the angle theta, all divided by 4 pi epsilon naught r squared. So much better. Okay, so we did the math, we got a formula. That's great, but what does it actually mean? What's the physical story this equation is trying to tell us? Let's move on and translate this math into some real-world meaning. This right here is maybe the most important feature of a dipole. For a single isolated charge, the potential gets weaker proportionally to 1 over r, but for our dipole, it weakens as 1 over r times squared. That means a dipole's influence fades away much faster as you get further away. And the reason is pretty intuitive. From a long way off, the positive and negative charges start to look like they're right on top of each other, and their effects almost completely cancel out.
Now, our formula has that cosine theta term in it, which tells us the potential isn't the same in every direction. It actually depends on the angle. So a pretty natural question to ask is, what's the potential at some specific, easy-to-define spots around this dipole?
Let's look at two really special cases. First, the axial line. That's the line that goes right through both charges. If you're on the side of the positive charge, theta is 0 degrees, and the cosine of 0 is 1. This gives you the maximum positive potential. On the negative side, theta is 180 degrees, cosine is -1, and you get the maximum negative potential. Makes sense, right? Now for the really cool part, the equatorial plane, which is a plane that slices perfectly between the two charges. Here, the angle theta is always 90 degrees. And what's the cosine of 90? It's 0. So the potential anywhere on this entire plane is exactly 0. That's because any point there is the exact same distance from both the positive and the negative charge, so their effects cancel out perfectly. To really feel that 1 over r squared relationship, let's just plug in some simple numbers. Imagine you're 10 units of distance away from the dipole. The potential is going to be proportional to 1 over 10 squared, or 1/100th. Now let's say you double your distance to 20 units. The potential drops to 1 over 20 squared, which is 1/400th. You see that. You doubled the distance and the potential dropped by a factor of 4. That's the power of that inverse square relationship. We have covered a lot of ground, from the basic definition all the way to a final formula and what it means. So let's wrap this all up with a quick, concise summary of the most essential things to take away from all this. So, what are the crucial points to remember? Number 1, our whole derivation is built on the superposition principle. Number 2, our final powerful formula is V equals P cosine theta over 4 pi epsilon naught r squared. This tells us the potential depends not just on distance, but also on the angle theta, and that it falls off really fast as 1 over r squared. And from that, we found our two key special cases. The potential is at its strongest along the axis of the dipole, and it's exactly 0 everywhere on that middle equatorial plane. And that brings us to one last really interesting question to think about. We just proved that the electric potential, V, is 0 all along that middle plane. So, does that automatically mean the electric field, E, is also 0 there? Remember, the electric field is related to the force a charge would feel. If you placed a little positive test charge right on that plane, would it feel a push or a pull? That's something to chew on. Thanks for joining me for this explainer.